So, happy Monday, everybody. Before we talk physics today, I thought we would talk a little bit about the test that's coming up on Friday this week. Hopefully everybody knows we have our third test coming up this Friday. So this is just the same test logistical info that's been up in Canvas the whole time, and I just updated it slightly for test 3. The main things I changed was I changed the date, of course. I changed the material, so as you can see, it's going to be on chapter 7, which remember was linear momentum, H8, sorry, which was all our rotation, so torque and angular momentum and rotational kinematics and all that. Chapter 9 was stress and strain, and then chapter 11 is our fluids chapter, and so it's just the parts of the fluids chapter that are on static fluids, so not moving fluids. Okay, so that's what it's on. You don't have to upload a selfie again. Everything else is the same here. Make sure we can see you on Zoom, all right? And make sure you do not have earphones, headphones, earbuds on. There were some people that had those last time, so please don't let that happen again. Make sure you're not talking during the test. That's another request, please. And then the other thing is that we are going to try this time to do the long problem first, okay? So it'll be a long problem that you'll get to do and write up, and then followed by 5 or 6 multiple choice questions. I haven't decided exactly how many yet. Okay, so that's what it's going to look like. I think that's everything. The other main thing is if you have any kind of connection issues while you're taking the test, while you're uploading, to please let somebody know right away. If it's during the test, we can give you more time. And if it's during the upload, we can also give you more time, or you can email your upload to me. So just the main thing is to let us know, okay, if something happens, so that we can do something about it. Okay, so that's all I wanted to say about our third test. So I'm going to stop sharing that, and we will switch over to our slides, unless anybody has any quick questions about any of that. And remember, the best place to ask logistical questions about the test, about when homeworks are due, things, is Piazza. Okay, asking those things during lecture is not great because Rasul can't answer those questions, and I'm usually wrapped up in talking and lecturing. And so that's just not a great time to ask those questions, at least not during. You could ask them at the end, okay? So we are moving on to chapter 12, which is all about what's called simple harmonic motion, which is what happens when you put a mass on a spring, ideal massless, frictionless spring. And I couldn't find a good spring comic, but I did find this cartoon. Some of you guys might recognize this. This is Wile E. Coyote. Let's see if this works. And Wile E. Coyote is famous for using springs. So here he is, trying to take advantage of spring potential energy. He's waiting for the Roadrunner. But it doesn't work out so well for Wiley. So, but in general, springs can be quite useful. So, and they're a nice, simple example of what's called a simple harmonic oscillator. As you'll see, if you ever go on in physics, lots of different physical systems can be modeled as simple harmonic oscillators. Oops, I didn't want that to start again. Okay. And a simple harmonic oscillator is something that undergoes what we call simple harmonic motion, all right? So because it's a nice, simple system that we've already looked at a little bit, we will mostly contain our discussion, at least today, to looking at a mass on a horizontal massless spring. And then on Wednesday, we'll look at pendulums of different kinds, which also, under certain conditions, exhibit simple harmonic motion. So as we know, if you have a mass on a spring and you extend or stretch your spring a little bit, then the spring will exert a force on the mass. Basically, it wants the mass to go back to the equilibrium position where the spring was not stretched. So you get a displacement x like this. In this case, it's a positive displacement, okay? And we say that the spring force, so this is in one dimension now, so we're using the positive, negative signs to represent our directions. So here, with a positive x, we get a spring that points in the negative direction, pointing back to where it came from, right, to the equilibrium position. And we know that the spring force is equal to minus kx, right? So it grows with the size of this displacement from equilibrium. But we also know, right, if this is the only force acting, if this is the net force on the mass, that force is equal to the mass times the acceleration in the x direction. So you could see in this particular case, since the force is in the minus x direction, the acceleration will be in the minus x direction, and the x component of the acceleration, then you can solve for what it is, because if minus kx equals m times ax, then that means that ax is minus k over m times x. So you can see it has a negative value when x is positive. Okay, and it depends on the ratio of k, the spring constant, to m, the mass on the spring. So, and like I was saying, in this case, this is a negative acceleration, and it's pointing towards our equilibrium position. And we're going to see that that's characteristic of this motion, right? That your acceleration, no matter which side you're on, will be pointing back towards equilibrium. So, for example, we could instead look at what happens when you compress your spring. So you take your mass and you push on your spring. And then you compress your spring, and now the spring force is in the opposite direction, again pointing back towards equilibrium. So now we have a spring force in the positive direction, okay? And that's because our displacement x is now negative, right? Because we compressed our spring. And so we can write the same expression, essentially, that F spring equals minus kx. We just have to remember now x is the negative number. Okay, so now that leads to a positive spring force in the positive direction. Okay, and similarly, since x is negative, that's going to lead to a positive acceleration. So acceleration in the positive direction, same direction as the force, like we would expect, right? Because again, net force equals mass times acceleration for that mass on the spring. So again, we have our positive x acceleration, right? Again, back towards equilibrium. So that what's happening, as you can see, is we're always accelerating back towards equilibrium. And that means that if you were to either compress or stretch your spring and let it go, it undergoes this oscillatory motion because it's always accelerating back towards the center. Okay, so if you pull it out and you start it at rest and you let it go, it accelerates towards the center, but when it gets to the center, it's moving with some velocity, so it passes the center, and then it decelerates, right? Okay, which essentially is accelerating back towards the center, right, until it comes to rest, and then it turns around and goes back and accelerates towards the center, and then it has a maximum velocity when it hits equilibrium, but then it keeps on going. And so you have this oscillatory motion back and forth, okay, because of the nature of the spring force, because it depends on position like this. And we call this motion simple harmonic motion. And we characterize it with a period, t, which is the time it takes for the mass to undergo one complete oscillation and get back to where it started. So it starts at one side, goes all the way over, comes all the way back. That's a complete oscillation. And that time is one period, which we use capital T. And it's equal to 1 over f, the frequency of the motion. okay, where the frequency is how many cycles per second. And we've run into period and frequency before when we were looking at things moving in circles. And then the other quantity that we like to define here is the amplitude, okay, A, which is the maximum x value you can get measured from equilibrium where x equals 0. Okay, so that maximum x value, and your mass basically goes, as we're going to see in a second, it's going to go from plus A to minus A, from plus A to minus A, and that A is the size of the maximum x displacement for a given oscillating mass on a spring. So those are our basic characteristics for our simple harmonic motion. So any questions on how that works? Okay, so if no questions, I think I have a question for you. So let's set up our poll here. So we actually have 5 choices this time. So okay, so here's our question. So we have a mass on a spring undergoing simple harmonic motion, like I was describing, and this motion has an amplitude A and a period T. What is the total distance traveled by the mass after a time interval T? So after 1 period. So that's our question. So think about what the motion looks like. Think about what T means, the period. So imagine like either compressing that spring or stretching that spring and letting it go, and looking at the total distance it would travel when it does 1 complete cycle, right? Because that's what a period is 1 complete cycle. Okay, I think we're going to do about 10 more seconds for this one. So go ahead and guess if you're not sure. All right, 5, 4, 3, 2, 1. So let's see what everybody thought. So we have almost a tie. So we have almost equal number of people voting for D, that the total distance will be 2A, and E, that the total distance will be 4A. And then we also have some votes for A and a few votes for A over 2. So let's have a look and see how this would work. So let's get rid of that. All right, so We're trying to figure out the total distance traveled after a full period of time. So here is our x-axis now with our amplitudes labeled. Okay, so remember that the amplitude was that maximum x. Okay, and so our mass is going to move from A to minus A and back again, right? Depending on where it starts. Okay, so say it starts, for example, at x equals minus A, then it's going to travel from minus A to A, and then back to minus A again in one period. Okay, so it's going to go 2A in the forward direction and then 2A in the backwards direction. So the total distance it will travel is 4A. Okay, any questions on how that works? This is basically just understanding what we mean by the amplitude of the motion, that it's that distance, right? It's how far you're displaced from equilibrium. So in fact, it doesn't matter where you start in the motion. You started in the middle, right? Say you started the mass in the middle with some velocity, like you gave it a push, for example, then it would move A, then 2A, and then another A to get back to the middle again, right? And complete one cycle. All right. So now what we're going to do is we're going to look at a vertical spring. So before we go on to analyze this motion in more detail, you probably, or you may have done a lab at some point with springs, all right? And probably in that case, instead of doing a horizontal spring, which is kind of hard to do without friction because you have to put it on a surface, so instead, we often do vertical springs. So, and if you hang a mass on a spring, it's going to stretch the spring because there's another force involved now. There's the force due to gravity. We know that there's the weight, right, pulling down. And if you just hang a mass on the spring and you let it come to rest, it comes to an equilibrium point where the size of the spring force up is equal to the weight down, much like we saw when we were talking about spring scales and spring balances, when we were talking about apparent weight and riding in elevators earlier in the course. So we know that when it comes to rest, the magnitude of the spring force is equal to the weight of the object, mg. And if we plug in that the magnitude of the spring force is k times x, where x is the displacement of the spring from equilibrium, we find that we can figure out exactly where this x point is, basically how much does the spring get stretched, okay, when you hang that mass on the spring. And it's just equal to m over k times g, our acceleration due to gravity. So what happens is, in the case of a vertical spring, because this is the point where the net force is 0, because now we have the two forces, the spring force and the weight pulling on the mass, this is our new equilibrium position. So for a vertical spring, this equilibrium position, this new one, okay, this is the point about which the mass will oscillate, okay? So it doesn't oscillate about the x equals 0 point, the unstretched or uncompressed point for the spring. It oscillates at a slightly lower point, depending on how much mass you put on the spring. But otherwise, it will undergo simple harmonic motion. So even though we've got two forces acting here and not just the spring force, the net effect of gravity is just to shift the equilibrium position down. That's all it does. Okay, so I thought we would look at our PHYS to see what this looks like. So we're going to switch over. So there's a really nice spring PHYS that I'm going to show you. And so this is, again, this is a vertical spring, which is what we're talking about here. And what I've done already is I've already hung the mass on the spring. Okay, and what you can see is I can turn on what's called the natural length point here. And so this shows you basically the point where the spring would be neither compressed nor stretched. So you can see with that green arrow that our mass is displaced. It's below the equilibrium point you would have if the spring were horizontal. And the actual new equilibrium point is represented by this black line here. They call it the mass equilibrium in this. So this is the point. This black line, as we're going to see in a second, that's the position about which our mass will oscillate. Okay? And then if I pull my mass down, you can see I increase my displacement of my spring. And then if I let it go, it will oscillate back and forth. And I'm going to slow it down so you can see that it oscillates equally above and below that black line. So it undergoes simple harmonic motion about this new equilibrium point, which is where the mass would hang if it were at rest. Okay, if you were to hang the mass on the spring and let it come to equilibrium. So that's the point right here. Oops, no, can I go back? So basically when it's right here, that's where the force due to gravity and the spring force balance each other out. And then the other thing, oops, I stopped it going. The other thing I wanted to show you is if you look over on the left, we actually looked at this simulation before when we were looking at the energy in a spring, because we did already talk about the energy in the spring earlier in the course. And what you can see now is that there are 3 types of energy going on here. I'm going to stop it for a second in the middle of its cycle. Right? We've got our kinetic energy due to motion, our 1/2 mv squared, our gravitational potential energy, which is the darker blue color. And the way that's measured in this simulation is they're measuring the height for gravitational energy relative to this blue line at the bottom of the screen. Okay, so it's positive because we're above that blue line. All right, and then the elastic potential energy, the lighter blue color, is because the spring is stretched. And then we can watch it go. And we can see when we get up to the top point here, where we'll get to the point where the spring's not stretched or compressed, right here, okay, then all we have, if it's at rest, all we have is gravitational potential energy and no kinetic energy and no elastic potential energy. And if we start it there and let it go, then it will oscillate back and forth again. Okay, so you can see what this motion is like. And this is kind of a fun thing to play around with if you want to try and understand what would happen under different scenarios. So the light blue one is elastic potential energy, and the darker blue one is gravitational. It's kind of hard to read, but it says PE grav and PE elastic there. We're going to go through. So let's talk about the energy here. Okay. So, and we have seen this before, right? Okay, so the total mechanical energy now for a mass on a spring is a sum of the gravitational potential energy, the spring potential energy, and our kinetic energy. Okay, this is our linear or translational kinetic energy. There's no rotation going on here. Okay, and so what do these quantities look like? So our gravitational potential energy is mgy, where again, as always, you have to pick a point to measure y from. Okay, you can pick a point, the lowest point of the mass. You can pick some point on the ground. It's your choice where you pick your y. Just once you choose a point, you want to stick with it. And then the spring potential energy is 1/2 the spring constant times how much the spring is stretched or compressed, x. That displacement, and this is the displacement from the original equilibrium position. Okay, right? This is the displacement from the unstretched, or uncompressed length of the spring right, if there were no gravity there. And then our kinetic energy, of course, is our 1/2 mv squared. So if you have a horizontal spring, which we'll look at a lot as well in this chapter, then you don't have to worry about the gravitational potential energy because it'll be a constant, right? That mgy would be the same the whole time, all right? So you can just essentially ignore it. If you tried to do conservation of energy, it would show up on both sides and would cancel out. And so we just get 1/2 kx squared plus 1/2 mv squared. And it's easy to show that this total will be equal to 1/2 k times the amplitude squared. Because if you think about when the mass is at either extreme of the oscillation, it comes to rest when it's at the biggest x, when it's at x equals a, or the smallest x, x equals minus a. And so all of the energy is going to be in spring potential energy at that point when it momentarily comes to rest at the peak of one of its cycles. Okay, and so basically when x equals a, v equals 0, and your total energy will be 1/2 ka squared. Yes, x is where there's no effect on the spring from gravity, exactly. Okay. So now what we're going to do is we're going to talk about what's called the reference circle. And so they did this in the pre-lecture, but I'm going to go over it again because I think it needs more explaining. And it's once we understand the reference circle, it's really, really powerful for analyzing a mass spring. Okay, so now it turns out, and this is kind of fun to show with a demo with the shadow of a mass moving in a circle and a mass on a spring, that the one component of the position of an object moving in uniform circular motion, so if you look at either the x component of the position or the y component of the position, in our case we're going to look at the x component of the position, that component undergoes simple harmonic motion. So for example, in this case, I've lined up a mass moving in a circle, undergoing uniform circular motion, so it has a fixed omega, okay? And the circle has a radius a, okay? And that, as we're going to see, that radius a is the amplitude of the motion for the mass on the spring, okay? That you can show that if you start this mass moving in a circle, so you start your little blue ball moving in a circle, okay, at the right angular frequency, that the position of the blue ball will match the position of the mass on the spring, that they undergo the same oscillatory motion with the same position versus time and acceleration and velocity versus time. Okay, and because of that, because these two motions track with each other, because mathematically the same thing is going on when you look at the x component of the motion of the blue ball moving in a circle and the mass moving one-dimensionally along the x-axis, right, the mass on the spring, you can use what we know about circular motion to analyze and come up with equations of motion for the mass on a spring. So that's why this is useful. So first thing we have to realize, okay, is that we're going to start with the case where, as you can see here, right now our ball is at some angle theta. Okay, our ball has undergone an angular displacement theta. Okay, so if that's theta, right, then that means that theta must have been 0 at time equals 0, right? And then at some later time it's at this angle theta. So we're going to say theta is 0 at time equals 0. What does that do for us? Well, remember, angular velocity is angular displacement over time elapsed. Okay, and if theta is 0, time equals 0, that means omega is just theta over t. So it's just this angle displacement from the horizontal, from the x-axis here, divided by the time elapsed, which means we can write that theta is equal to omega t. And that's going to be useful. All right, so that's how theta varies with time. Our angle theta varies with time in that it's just the angular velocity times the time elapsed. So first thing we notice here is if we look at the right triangle in the circle, that x component of the motion is just a, the radius here, or the hypotenuse of that right triangle, times the cosine of theta. just like x often is, right? And then we can plug in that theta is omega t, and we get an expression for how the position, okay, of the x position of the ball changes with time. It's also an expression for how the x position of the mass changes with time. Okay? Now we're going to look at velocity. All right, so that's position as a function of time. Now we know for our mass moving in a circle that we have this tangential velocity. Remember, this is uniform circular motion, so it's a constant magnitude speed, just the direction is changing. And since the direction is changing, the x component will be changing, and the x component of this tangential velocity represents the velocity, the x component of the velocity of the mass. Okay? So we're going to draw our right triangle here for the velocity, okay, to figure out what's the x component of the velocity, because that will be the velocity of our mass on the spring. And we can see now the angle theta is in the upper corner, the upper left corner here. Okay, you can do a little bit of geometry to prove that that is the angle theta. And the other thing to notice is that the x component of the velocity is in the negative direction. And so we get that Vx is minus V, and because theta is in the upper left here, it's minus V times the sine of theta. Okay? And now we plug in that theta is omega t again, and we get an expression for how the velocity in the x direction changes with time. We're going to do one more thing though, because we don't know what V is yet, but we can figure out what V is. Right? Because V is just that tangential velocity for an object in uniform circular motion, and we know that's just equal to the radius of the circle, A, in this case, times the angular velocity. So we can plug that in for V, and we get an expression for the x component of the velocity, which is the velocity of the mass on the spring as a function of time. We get minus A omega sine omega t. All right, so the position goes as a cosine, the velocity goes as a negative sine times this A omega quantity in front, which we'll come back to later. But you can see that A omega quantity is that tangential velocity for the ball moving in a circle. It's actually the maximum value for the velocity of the mass on the spring, right? Because the maximum value happens when the mass is at x equals 0, right? And that's when x equals 0, right? You're at the top of the circle, okay? And that's where theta is 90 degrees. The last thing we're going to look at now is acceleration. So we know for a mass moving in a circle, or a little blue ball moving in a circle, the only acceleration happening is centripetal acceleration. So I've drawn in my centripetal acceleration there, pointing in towards the center of the circle, and now I'm going to draw it again down here, because again, what we want to figure out is how does the x component of the acceleration change with time, because that will tell us how the acceleration of the mass on the spring changes with time. So now theta is in the upper right here, okay, so that means that the x component of the acceleration, again, it's another negative one, just like velocity was. We have a minus sign times the magnitude of the acceleration, which is our centripetal acceleration, times, again, the cosine of theta. So it's minus A cosine, plug in omega t for theta again. We get minus A cosine omega t. Now we want to figure out what's the maximum value the acceleration can take on. We're just going to use our expression for centripetal acceleration. And our expression for centripetal acceleration, you might remember, for an object moving in uniform circular motion like this, okay, or any object moving in a circle, the centripetal acceleration can be written as the radius of the circle, which in this case is our amplitude, times omega squared, right? You can derive that, right? Because remember, centripetal acceleration is v squared over r, right? But we know that v is a times omega. So we plug that in for A, for the maximum value the acceleration can take on. And so this is the value the acceleration takes on when your mass is on the spring is completely stretched or completely compressed. it will be equal to a omega. And so you get this expression for the acceleration as a function of time minus a omega squared cos omega t. And so now we have three expressions, okay, for position, velocity, acceleration as a function of time for a mass on a spring. Okay, and these will be very useful for figuring out what the motion looks like and finding where the mass is at some time. All right, so it looks like Rasul is answering people's questions, so that's good. So what we're going to do now is do one more step here, which is to look at our x component of the acceleration and our position as a function of time. And notice that they're both cosines, okay? And so we can, in fact, plug in for that omega t, for that cosine omega t, or a times cosine omega t, right? And you can show, essentially, by equating these two, right, by plugging in for x here, that ax is a minus omega squared times x, okay? And that's true all throughout the cycle because they both vary like cosines. One's a positive cosine, one's a negative cosine. No matter where you are in the cycle, ax depends on your position, okay? It's always minus omega squared times your position. All right, but we showed earlier that ax for a mass on a spring has to be minus k over m times x. And so now combining these two equations, we can see that that means that omega squared, which remember was the angular velocity for the ball moving in a circle, is equal to k over m, the spring constant divided by the mass. All right, and now omega, right, which we talk about as angular velocity when something's moving in a circle, is actually, you can also refer to it as angular frequency, all right, because it's equal to 2 pi times the frequency of the motion, okay? Like we used to talk about frequency with something moving in a circle of how many times, like how many revs, right, per minute or per second, and that would be the number of revs per second would be your frequency. So it's similar here, right? The frequency is the cycles per second, and so omega 2 pi times that gives you your angular frequency, and since frequency is 1 over period, you can also show that omega is 2 pi over the period. Okay, and then we combine that with our velocity equation, and again, we've got our three expressions for how these things vary with time. And so if you were to draw graphs of them, they would look like this. So here's our cosine for our position in blue, and the green one is our velocity, which is a minus sine graph. And the last one, a minus cosine graph, that's how acceleration varies with time. Okay, and the things to notice, all right, notice that the velocity varies between a times omega and minus a times omega, because a times omega is the maximum value the velocity can take on. And similarly, the acceleration graph varies from omega squared times a to minus omega squared times a. Okay, because a omega squared is the maximum value the acceleration can take on. And the other thing I wanted you to notice is that just like from way back at the very beginning of the class, it's still true that the velocity is the slope of the position versus time graph. If you look on the position versus time graph at the points where it's 0, okay, you'll see the slope on the velocity versus time graph is horizontal, right? That the slope is 0, that the graph is horizontal, okay? And for those of you who are good at calculus now, we know that velocity is in fact dx dt, the first derivative of position versus time. And you may know that if you take a derivative of cosine, that you get minus sine. And then similarly, acceleration is the slope of the velocity versus time graph, okay? And so likewise, if you go and look at where the velocity versus time graph is 0, you'll see that that's where the slope of the acceleration versus time graph is 0. And similarly, acceleration is the first derivative of velocity versus time. If you take a first derivative of velocity here minus sine, you get a minus cosine. So this is consistent with calculus, as it should be, and it's consistent with our understanding of how these different graphs relate in terms of their slopes. So I know that was a lot to take in. That took a little longer than I thought it would. Okay, but it's important to understand how this motion works, all right, and how to use these equations for the different quantities versus time. All right, so I think now I have another question. Yes. So after all that, we're going to try a poll question. And yes, it is important to know how to draw these graphs. And we're going to actually analyze a graph here. So let me put in these choices. Okay, so what do we have here? So we have, so this is a displacement versus time graph. So x is the displacement from the equilibrium position for a mass oscillating on a spring, okay? And at a certain time, the displacement of the mass from its equilibrium position is indicated by the point P on the graph. All right, so we're looking at just after 2 seconds is where the point P occurs here. Okay, and the question is, which of the following statements correctly describes the signs of the velocity and the acceleration of the mass at that time? So we have a position versus time graph, and now we're trying to understand what do the velocity and acceleration look like at that point. Okay, so our choices are that both the velocity and the acceleration are positive, that the velocity is positive and the acceleration is negative, that the velocity is positive and the acceleration is 0, that we have a negative velocity and a positive acceleration, or both the velocity and acceleration are negative. So think about a mass oscillating back and forth, okay? And where we are in the cycle, and what the slope of the graph means. Someone wants me to go back to the last slide, so I'm going to go back to the last slide. Looks like that. All right, now we're going to go forward again. Okay, I think we're going to do 10 more seconds on this one. So if you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. All right, so what do we have? So we have a lot more agreement this time around. So a large group are saying that the velocity would be positive and the acceleration would be negative. And then we have a few votes for that they're both positive. So let's have a look. All right, and so what do we have? So first thing to notice is that at point P, the slope of position versus time graph is positive. So that means that the velocity will be positive. And then the next thing to notice is that the slope is decreasing as time goes on. Okay, and since the slope is decreasing, right, it's starting like this and then heading towards a slope of 0. Okay, and since the slope is decreasing, that means that the speed is decreasing. And since we're moving in a positive direction and decreasing, that means our acceleration will be negative. Okay, so you can actually analyze this, right, just by thinking about what we know about graphs and what of these position versus time, and what we know about what the motion looks like, and what the shape of this curve tells us about the motion. All right, so you don't necessarily need to use the equations to work these things out. You need to think about what's happening with the motion and use that, okay, to figure it out. All right, so I'm running out of time, but I really wanted to start at least this sample problem. And what I may do is if I run out of time, I will keep going and record it. And if you have to leave, that's fine. And you can come back later and check it out and watch the end. Okay, so what do we have here? We have a 0.63 kilogram mass, and it's suspended vertically from a spring with a spring constant of 24 newtons per meter. The mass is raised 14 centimeters above the equilibrium position and then allowed to drop. Okay, and what we're going to figure out is what are the frequency and period of the resulting simple harmonic motion, and we're going to calculate the velocity and acceleration 1.5 seconds after the mass is released. So that's what we're going to do here. So like I said, I'm going to start this. I'm going to switch to my document camera. And if you have to leave, that's fine. And I will just make sure it gets recorded. All right. So first, we're trying to figure out what's the frequency and what's the period of the motion. And we know they're related to each other. So once we get one, we can get the other. Okay, so how do we get these? Well, we can get them from angular frequency, omega. And remember, we had omega squared was equal to k over m. So that means that omega is the square root of k over m. And they gave us the k, and they gave us the m. So the k was 24 newtons per meter, and the m was 0.63 kilograms. All right, and so that tells us what this angular frequency is. Okay, so that gives us an omega of 6.172, and our units here, as always for omega, would be radians per second. And that is equal to 2 pi times the regular frequency of the motion. So that means we can figure out frequency here by just dividing both sides by 2 pi. And if you do that, you get a frequency of about 0.982 hertz. Okay, so that's the frequency. And then to get the period, right, we just do 1 over the frequency. And if you do 1 over that number, you get about 1.018 seconds, right? Because a hertz is 1 per second. All right, so that's almost always the first thing you're going to do with one of these problems is you're going to take your k and your m and figure out omega, because omega then will tell you the period and the frequency. All right, or sometimes they'll give you period or frequency, and they'll give you, say, k, and you have to figure out m, or they'll give you m, and you have to figure out k. That's very typical. All right. Okay, this is just omega divided by 2 pi. All right, so now the next part of the question was, how do we find the acceleration and the velocity at time equals 1.5 seconds. So we want to know what's the velocity equal to. I'm going to call it Vx because we were calling it Vx before. And what's Ax equal to? Okay. At time equals 1.5 seconds. All right, so how are we going to figure that out? Okay, luckily, for this particular scenario, with our mass on our vertical spring like this, okay, we started, they told us where we started, okay, they said that you pick it up 14 centimeters, okay, so we call this our x-axis. We're starting at x equals 14 centimeters, which is 0.14 meters, okay, so that's going to be our amplitude. All right, because we started there, and then it's going to oscillate back and forth between plus and minus a, like that. That's our amplitude of our motion. All right, and since it starts at a positive x like this, this one is following our cosine curve. Okay, so this is a case where x equals a cosine omega t. Now we're going to see next time that not everything follows this exactly. Sometimes there's what's called a phase angle, so we don't always follow exactly a equals cos omega t, but this one does, so we can use this formula. Okay? And that means that our Vx is minus a omega sine omega t. That was the formula we had for our velocity as a function of time. And we're just trying to figure out what's the velocity at 1.5 seconds. Time equals 1.5 seconds. So we just have to plug in that time to solve for it. Okay, and so I'm going to write it here with a bit more space. Okay, so what do we have? We're going to plug everything in we know. Our amplitude is our 0.14 meters. Our omega, which we wrote up here, is our 6.172. And then it's the sine of omega, again, 6.172 times the time, 1.5 seconds. All right, so we plug all of that in. It's all in SI units, okay? So it will sort itself out to be meters per second. And if you crank that through, you get minus 0.143 meters per second. Okay, so we've got a negative velocity. All right, so that means it's moving in the negative direction. Okay. Don't worry if you have to go, it's fine. Because like I said, I'm recording this and you can watch the rest later. And we're almost done. We just have to figure out acceleration. So our expression for acceleration is minus a omega squared cosine omega t. And we plug in all our values, 0.14 times 6.172 squared times the cosine of 6.172 times 1.5. Okay, and we crank that one through, and we're running out of space here. Give myself a little bit more space, and we get the exponent of the acceleration. Now, it turns out this cosine, remember this, really, really important, this is in radians. Forgot to mention that. Okay, really important to realize that this is in radians. Okay, remember this was in radians per second, this is in seconds. Okay, so it comes out in radians. Okay, and we get this one, because this cosine is negative, our acceleration becomes positive. It's about 5.26 meters per second squared. So this is our x velocity. This is our x acceleration. And we could also solve for our x position if we wanted to. Okay. And that's how you would use these formulas in a problem. And like I said, we'll talk more about this next time, but I'm going to finish up there. Okay, and we'll talk a little bit again about this as we go on beyond the sine and cosine formulas and add in a phase angle. Okay, I'm going to stop recording now.